Welcome to week 9. We're looking at vibration isolation, and here's some isolators, vibration isolation devices, kind of small. Here's little small ones that have also have some damping characteristics in them, but most of the time you'll see vibration isolators that are more just basically springs. This is notable. They have springs inside of a spring. That's an interesting. And sometimes they'll even have one spring is shorter than the other spring when you do that nested spring thing. So the spring constant will actually change after a certain amount of displacement. Kind of interestingly. Here's the same thing, except we're mounting off of an overhead for these might be pipes or ducts or some. Usually a lot of times pipes being hung. They don't see the pipes in there, but that's how they get hung. Here was a job I did involving some vibration mounts. It was poorly executed. If you could see this little video, little picture right here, you can see that some of the mounts were actually in between stiffeners. That was not a really good deal. It made the deck between the stiffeners deformed. Here's some other things. I've posted these. These are from Dr. Bob about poorly installed vibration isolators. Some bad ways to use some vibration isolation techniques. So read these up. You could read the captions. I'm not going to read them for you, but interesting to sometimes to see what's done, what people have done wrong, so that we can learn to do the things the right way. Yeah, well, here's an interesting one. We need some flexibility in the electrical conduit right there, right? So the vibration isolators allow some amount of displacement. We can't forget to include some slack into like cables and that kind of thing, or even piping that might be attached to it, or tubing or other things. Someone has gone and put in some spacers here where that's supposed to be a gap that opens and closes. So that's sort of an important thing. I guess they're supposed to remove that after adjustment here, that steel spacer. So there you go. That's what that's about. And we could have the isolation of pieces of equipment, especially something like an air conditioner that might be on the top of a building, or and that can transfer, have a noise pathway that can go through the into the structure and cause people some misery. Here you go, putting the little pads underneath I guess this is a continuation. So this is just a real picture of this schematic of that situation. All right, so here's the stuff that we need to cover as part of this introduction. I think the most important thing to look at is this phase diagram right here. We can see that, or maybe the big concept here is that now we're going to be looking at what happens to this as opposed to what's happening to this, right? Because we want to have the vibration isolation. Previously, it just looked like it was planet Earth is connected to, but you could have some type of structure like this where that vibration is going to be pushed down to there. So our main goal is to look at the transmitted force, FT. How much of the force, like this is, so you can think of this as the input, right? This guy right here is the F is equal to FO times the sine of omega FT, and you could also put a phase angle in there if you wanted to. Probably we usually don't do the phase angle thing, not for the input. That might be what we reference to later on when we go to see what the output. And so the output is this portion right there from this point of view. And if we're going to make some kind of silly looking FBD, we would say, well, let's just make the force due to the spring right here. It's called, this is like one of the forces to the spring. That's this guy. And then we have another force of the spring right here. Now, right here, excuse me. But this one, we've been using red too much. Let's go to blue. This guy right here, we show him as acting at the same time, but he's not actually acting at the same time. He's this guy right there, right? That's going to be, the damper force is going to be C times the velocity which is omega f times the displacement of this piece, right? So whatever this magnitude of the displacement is going to be put right into there. And so the reaction that we have right here, or the thing that we're pushing back, is this Ft, right? Because so these don't actually add. They actually they add as vectors, because right there I will switch back to red so that I can say that that is the spring force that's happening in here. And so here is the results, right? So that right there is the concept that we're dealing with vibration isolation. It's the square root of these things squared so that we can get the hypotenuse in this phase or vector diagram that kind of explains the phase, that the two, the spring and the damper, are 90 degrees of phase away from each other. And then we could go ahead and do a little bit of math, separate out. We really like it. We know that that's going to be R right there. And then we combine this with our good friend. So this one is just a recall to look at an equation that we've been using a lot, which we also, excuse me, like to put in here and go square root of 1 minus r squared plus 2 squiggle r whole thing squared, right? That's a very familiar equation to us. So let's take this, take a look at it. We have an x right here and an x right there. So we can combine those two, and our goal then mathematically is to link together those two, because this is the input, and for our purposes here, that's the output, right? So this is the input right here, that FO, and now we want to see what the output is, input versus output. And so we create this thing called the transmissibility that we'll use as a 2-letter variable TR, and that's simply going to be FT over FO. We could rewrite this thing out a little bit more compact. We note that we have here up on the numerator a term that looks a lot like one that's in the denominator. So here we go, right there. We have that one that we're used to, but this is looks a lot like the term on the top. Oh, and I made a mistake. This common most of the time. I put a minus in there. That should be a plus. So I just noticed it, so jumped over there. And we could easily see that if there's no damping, that we condense down, we get rid of that term and that term, and the only thing we left, we have we get rid of the square root type of thing. Is that true? Think so, yeah, because we have that square right there and nothing else, right? So this can also be 1 over r squared minus 1, which is interesting, that it is not 1 minus r squared, because we usually often see that. But I guess that's, we could move the thing around. I think the math works out, so that's true. But anyway, this is the Peter. There's an example later where I show that if you want to improve the transmissibility, if you want to reduce the transmissibility, because we don't want the T to be bigger than the F. I mean, you don't want the FT to be bigger than the FO. So if they want that to happen, this value TR needs to be greater than the square root of 2, and we'll show that in an example coming up that I took out of Beer Johnson. But this can be seen from, this is from Dr. Jasinski's notes. I think it's in the book somewhere too, but I took it out right here, that you can see your transmissibility, and you plot out this, and of course he's written it out like I did, except that he put 2 separate square roots in there. But you can see that right there is the square root of 2, or 1.414, right, is the square root of 2. So that's where If you are onto the right-hand side, you're improving transmissibility, but here on the left-hand side, you're making transmissibility worse, right? This is forecasting to another type of problem when you have rotating imbalance. You could actually have sort of the opposite type of thing taking place. But we haven't done this yet in this section, but it's something to consider. It's sort of an interesting thing that where our transmissibility is getting much worse in over to some of the places over to the right in here. Something to observe. All right, so we're going to do an example in the next section. So I'll stop here and then continue with the next video.